All right, let's finally start our proof that plus, as we have worked hard to build it up here, does all of the things that it's supposed to do. So let's start here. If you take two natural numbers, then their sum is a natural number. So consider any two natural numbers, m and n. Then if I take their sum, what order am I doing? M plus n. Then if I take their sum, m plus n, then that's add. That's adding n to m. By the way, if you're wondering why it sort of looks backwards, or if it gets flipped around here, it doesn't have to be. Like you can totally, since we're eventually going to define, since we're eventually going to prove this property here, that the order does not matter, you could totally say m plus n is add mn, and maybe that would be easier for you, but we're doing it this way. Pretty soon it's not going to matter. I like this approach because it sort of looks at m plus n as starting with m and then adding on n. So taking the m and then applying next n times. So I'd rather think of the thing on the left as what I'm starting with, and then the plus n is sort of doing something to it. Anyway, not important. So you choose one way and stick with it. We've chosen this way. So why do you think that this is a natural number? Why should we believe that this is a natural number? Well, it's an output of add n, right? So it's definitely in the range of the function add n. What I'm using here is this theorem 52, which really deserves a title. I don't know why it doesn't have one. Maybe it should be called essence of range or something like that, because it's how range ends up being useful, how the concept of range ends up being useful in the context of an actual function rather than just any old set of pairs. If you have a function, then for something to be in the range is the same as saying that it's just an output for some input, for something in the domain. So as long as m is in the domain, which it is, since add n, remember, we define add n to be a sequence of things in our set capital X back here, which was set of things from n to n. So the domain of add n, is the set of natural numbers. So definitely m being a natural number would be in the domain. So then this is in the range. When you input something, the output is in the range of the function. Okay, and what do we know about the range of add n? Well, again, remember add n maps n to n. This is because add n is in that function called x from our definition. So that means it maps n to n. So this range is a subset of n. So that's the reason m plus n is a natural number. So there's not really that much going on there. Sorry, I was scrolling it in the wrong place. There's not really too much going on here. The only reason we're putting it here is so that you don't have to go back and use definition 110 and use the definition of add, like here, in order to just know that the sum of two natural numbers is a natural number. So even short, very tiny things we're including here, just so that it doesn't require you to go back and ever look here again. You can just use these, mainly. Okay, how about this one? M plus 0 is m. So let m be a natural number. Then, what's m plus 0? It's add 0 to m, right? So that's, what's add 0? It's like the only one that I know directly, right? It's the identity. And that's just m. So this line is justified by the definition of add. This equality is justified, oh, I'm sorry, no. This equality is justified by the definition of plus. then this equality is justified by the definition of add, and then this equality is justified by the way identity works, so that theorem, facts about identity. Okay, so that's it for that one. They're all very small and follow pretty easily from what's coming above. Before we move on, let's just consider 0 plus m rather than m plus 0. What would this be? This would be add m to 0, right? Well, now it's not so easy, right? Because add m, I don't really know anything about this except through the recursion rule. And so if m is just any old natural number, then I'm not going to be able to prove anything about this, unless I use induction, which we'll use later. But you see how it's much more complicated to think about 0 plus m rather than m plus 0? We will deal with this later. It'll come up here as one of the things in the next theorem. But these are just like the basics, the super easy, immediate to prove things. Okay, let's work on part 3 now. So m plus the next of n is the next of m plus n. All right, so here it is for natural numbers m and n. We have this. So let's consider any natural numbers m and n. Then we need to prove this. So by the way, you're seeing me now use the word let. Hopefully you're aware that this is just a short way to say consider any. This is still setting ourselves up for the universal generalization, show that this is true for all natural numbers m and n. Let is just a pretty versatile short word or phrase for sentences like this. Okay, so how about we start with thinking about the left-hand side? I don't know if that's a good plan, but let's see where it goes. So then m plus next n, well, by the definition of plus, that's add next n to n, right? But then add next n, by the definition of add next n is the same as this. It's the same as taking add n and then composing with this thing. And then by essence of composition, this is all stuff we saw when we were proving that 3 plus 2 equals 5, right? We have this. And what are we seeing inside here? We're seeing m plus n, right? By the definition of plus. And what did I want to end up with? Next m plus n? Okay, yeah, I'm definitely there. So this is next m plus n because of the way this symbol works. As long as what I'm putting in really is in the domain of that symbol. And is it? Is this a natural number? Yes, absolutely, by part 1. So there are a lot of words that I'm not writing that justify each of these equalities, but hopefully because I'm talking through it, you're also seeing where they're coming from. Okay, so what we're seeing is actually what this equality here, m plus next n equals next m plus n, what this is doing is just capturing, using the plus notation, it's capturing the recursion rule. This is the fundamental step here, from here to here. All the other steps were just using the definition of plus to rewrite things from plus notation to add notation, and they were using the definition of this thing to bring in the next symbol into the picture. But the crucial step is this from here to here, where we applied the recursion rule in the definition for add. So you can think of this, idea here as the plus flavored way of writing down the recursion rule for add. Here is the recursion rule for add. And this is like the starting point for add, right? This one was just using the starting point. So this is telling you how to plus 0 You plus 0 by doing nothing. M plus 0 is n. And this is telling you how to plus next n. You plus next n by nexting the plus n of what you had. So right here, these two are just another way, a plus version of writing these two. Okay, and number 4 I really like, and I'll tell you why. So let's verify number 4 first. Next n is n plus 1, so let's see. Let n be a natural number. I don't know why I'm in green. Let n be a natural number. Then how about, instead of, if I start with next n, then I'm going to have to like build structures around it in order to get it to look like n plus 1, since next n is sort of the more primitive object in our language. I find it easier to start with the thing that's already built up and then break it down using the definitions. So let me start with n plus 1 instead of next n. So start with the right-hand side of the equal sign. Okay, that's a big structure that has stuff that I can peel off. So first of all, the plus is like this. This is add 1 of n, right? Add 1 of n. And add 1, let's break that down. So add 1 is add next to 0. Yeah, it's just that's what add 1 is. Add next 0, which is this composed with add 0. That's the recursion rule for add, which is this composed with the identity, which is this of the identity of n, which is this applied to n, which is, since n is a natural number, it's in the domain of this thing, so rather than a big error, we get next n. Okay, so n plus 1 equals next n. Done. So I really like this because we've had to write next n many times in the course so far, right? All this junk with induction here, every time we use induction, we use next n all over the place. Now we have the right to use this more intuitive notation, n plus 1. So from now on, you can and you should actually write n plus 1. If what you're working on comes after Theorem 12 Part 4, you should write n plus 1 rather than writing next n. So this is now a valid way to write the successor of n. And you'll see me do it when I do inductions to prove things later on, like here. I will write things in terms of n plus 1. So what I mean is, when you make your induction hypothesis, then what you want to prove is the same proposition, but with your x's replaced by n plus 1. Just a notation thing, but I like it. All right, and 5. So I'll let m and n be natural numbers. This is the global assumption for all of these, right? M and n are natural numbers. That's why I keep saying that part. So let m and n be natural numbers, and then let's start working with this. M plus n plus 1. Well, this is m plus, we just saw that n plus 1 is another way of writing next n, right? So by part 4, that's all it is. M plus next n, well, part 3 describes what that is. M plus next n is the next of m plus n. So how do you add next n? Well, if you know how to add n, then you just do that, and then you do another next. That's what this is saying. That's the recursion rule for add. And then, am I done here? I want to end up with n plus n plus 1. Ah, yes. So then, that's by part 3. So here I'm applying part 3. Here I'm applying part... No, I'm sorry, part 4. By part 4 here. By 4. So when I say by 4, what I mean is I'm using this fact that the next of something is that thing plus 1, assuming the thing is a natural number. The next of a natural number is that natural number plus 1. Next n is n plus 1. Next this thing is this thing plus 1. And here, what are we using? That one was 3, right? The recursion rule. Okay, great. So we've established all of these, and now we can, so there are two things we can now, there are several things we can now do away with. We can do away with all the stuff up here, by which I don't mean delete it from your language. I mean delete it from your immediate attention, at least after you've done any homework problems or quizzes having to do with it. Then you can delete it from your immediate attention and focus your attention on this for the rest of your work with plus. And another thing you can get rid of is actually next itself. You don't really need it very much. Maybe sometimes you'll need it if you do stuff with ordering up there, but you can write n+1 instead of next from now on.